molecular chemistry in terms of quantum quantum mechanics. So in this lecture, we actually looked at the feature. So in this lecture, we will look at the molecular spectroscopy view in respect of quantum chemistry. So, in molecular spectroscopy, we actually did do characterization of molecule in terms of absorption of light. Okay, so if you think, we know about the UV absorption and IR absorption kind of things that actually excited the electronic state as well as vibrational state. And if you do experiment with the in microwave region, you can excite the IR region. So, so you can think like that. If I draw a wait, so mhm. So in so as you can see, okay, so in a UV spectroscopy, if you excite a molecule, if this is a this is ground state, if you excite to its first electronic state, you can get the absorption spectroscopy that is corresponding to its electronic excitation. Now, if you zoom in to its only ground state view, you will get the excitation about its vibrational term. So it can be recorded using IR spectrometry. This is in UV region. Now, this you these vibrational levels are also embedded with the rotational states. So, so if you look at the particular rotational state, if you can see the in V0, there is multiple rotational states are there. Okay. So now you can also excite this rotational state. Okay. And build in B in depend on that there is another spectroscopy known as rotational spectroscopy that is in microwave range that is generated used to detect the rotational excitation in a molecule. So this is the view that we have already known about the molecular spectroscopy of a molecule. Now the thing is that I can depict all this picture based on the potential energy surface of a molecule. So that potential energy surface is dependent on the quantum is based on the wave function method or DFT method or anything. So this lecture actually tells about the quantum mechanical view of the molecular spectroscopy. So now, as the first two lecture actually shows you the how to deal with the how to we can in this lecture we will get the view how quantum mechanics come into the picture to decipher the molecular spectroscopy of a molecule. Okay, so you can see that the lecture has started with the time dependent Schrodinger equation and then derive with the time in and perturbation, and in perturbation how the molecule the excitation light is considered as a perturbation in the system, and how it excitation and changes the Hamiltonian and excite the molecule to its the excited states. Okay. So in the first two lectures, this is the first class, and I hope we get late to start these classes. So in this lecture, we actually go through the first, first two assignments. That is assignment 0 and assignment 1, as instructed by the courses. So we'll start with a brief overview so that we can finish with their time. So first, I have already prepared the slides for the first assignment 0 and 1, and today we will cover only first 1 and 2, 0 and 1 lecture. Okay, so with this, we can start lectures for 0 and 1. So, so let's start. So as you can see, the first question that is asked about the what is the correct statement, what is the, let me go to the first slide. What is the acceptable wave function among the following given wave functions that are provided in the question options? So first one is x e to the power minus x. So in x e to the power minus x. So and second one is x square e to the power 2 pi I x, and third one is sine inverse x within the limit of minus infinity to plus infinity, and fourth one is x to the power or mod x in range of minus 1 and minus infinity and plus infinity. Okay, so now the thing is that we actually now before going to the details of how to solve this question, we have to look at what is the acceptable rules of acceptable wave function. So for the rules, I can show you that the you can see in the slide. So in case of acceptable wave function, the psi must be continuous, and second one psi must be single valued, and third it should be quadratically integrable, and fourth the differential of psi should be continuous and psi should be normalized. So these four criteria is needed for a wave function to be acceptable. Because why we need this four criteria? Why we are considering about the psi? What is psi? Psi is a wave function of a electron that present one electron wave function. Okay, so it has all the information about the electron. Where is it? What it can gives is the all the information. And if you ask the what is the momentum, what is the kinetic energy, you can get it from within the psi. Okay, so, so now for a acceptable wave function, psi should follow these four equations, four rules. Okay, five rules. Okay, so now if I go for the first x e to the power minus x. So x e to the power minus x, if I draw, you can see you will get a expression like this. Now you can see at each point of x, their psi has a particular finite value, and after and it has a initial rise when x is increases, and after some time that e to the power minus x dominate over x, and it is decreases with following a exponential. So, so in every x, the psi x has a finite value, and all the four character it satisfies. So psi that at that in that in that point you can consider psi x, that is x to the power e minus x, is a acceptable wave function in between 0 and infinity. Now consider psi x squared minus 2 O pi I x. Okay. Now, if I take a probability of finding of psi in my 0 to infinity, what I have to do? The psi star x, psi x dx. Okay. So now, if I do it, you can see the you can see how I solved this equation, and you can see in between 0 to infinity the psi is not finite. Okay. And as I see told previously, psi should be single valued and finite between the minus infinity to plus infinity. Okay, so psi must be finite. That rule is not satisfied in these cases. So x to the x squared e to the power 2 pi I x is not an acceptable wave function. Okay, so now moving to the psi to the power minus x. So in psi to the power minus x, if I plot it, you can see the plot is looks like this, where it's extended toward minus infinity to plus infinity. So you can see that the sign is infinite is going infinite. So psi cannot be defined within this range. So that means the psi is not psi x is equal to sine to the power sine inverse x is not a acceptable wave function. Okay. So now the last thing is e to the power minus x mod x. Now e to the power minus x mod x, you can see the plot. So whatever minus x and plus x, the plot is look like the exponential decay based on your x value, and you can see the psi single valued psi should be normal continuous in between this range, and hence the psi x is acceptable wave function. Okay, so this is the answer of the your first question. So now moving to the your second question, the total number of distinct possible transition for a particle in 2D box, and Lx and Ly is similar. Uh, Lx with Ly, and energy level Ni is equal to 1, 2, 3. So this is a question for particle in one dimensional box. So in one dimensional box, you can think as a so in one dimensional box. The energy is written by n square a square heat m square, where n start from 1, 2, 3. Okay, so now n is the quantum number. Okay, so quantum number cannot be zero point 0.5, 1.5 like that. It must be integer. Okay, and it cannot be zero. Okay, for particle in a one dimensional box. Now the question that is come here, the number of distinct transition provided 2D box. So we have to consider for in a 2D box nx, ny. Okay. Now 2D box, but your Lx is equal to Ly. So this is a not a rectangular box, it's a square. Okay. So now, so you can write, okay, this is the energy for a rectangular box. Okay. Now the question says, what will be the possible transition for Ni 1, 2, and 3? So Ni 1, 2, and 3 on the quantum states. So what will be the possible quantum states? First, the question, first we answered that what is the possible quantum state? So for Ni 1, 2, and 3, the states will be 1, 1, 1, 2, 2, 1, and 3, 2, 2, 3, 1, 2, 3, 3, 2, and 3. So now energy axis. Okay. So now these are the energy level. So similar thing that I can say show here. So these are the 1, 2, 3, 4, 5, 6. That, and there is one should be there. And 6 energy levels are there. Now, once you get the energy levels, you can see that 2 1 and 1 2 1 2 and 2 1 1 3 and 3 1 and 2 3 and 2 3 2 are the same energy. That's why these energy levels are degenerate levels. Okay, because two energy levels having the having the same energy, that is called as degenerate states. Okay, so now on that point of view, now we have to look at the possible transition between these states, among these states. So now, before that, we have to look at the possible energy in between these states. Uh, Sorry, possible energy of this, the energy of these states. So you can see that from 1 and 1, that the energy will be T2E. Okay. So H, what I did, I take the H square 8 ml square as a consider it's a energy represented by E. So this energy is represented by E. So this thing is represented as E. Okay. So now for 1 and 1, the energy should be 2E. Okay. Now next, what is this? 1, 2 and 2, 2, 1. So what we will get? 1 square plus 2 square is 5, 5E. Next, the second state is 2, 2. So 2, 2 is 2 square plus 2 square. With this formula, it will be 8E. E1, 3 and 3, 1 will be the same energy. It will be 10E because D state, and D state both are degenerate. These all are degenerated state. Okay. Now, similar to 3, 2 and 2, 3, it's coming around 13, and E3 and 3, E3, 3 is coming 18. Now, these are the 5, 6 different energy levels. Okay. Now, now we have to look at what are the possible transitions. So now we can see that I have drawn whatever the possible transition is possible. Uh, you can see, so for 1 and 1, and so you can see the first transition can be possible from 1 1 to 3. Possible transition is 1 1 to 3T. So the transition energy is calculated is between delta E is energy of final state minus the energy of initial initial state. So for E33, sorry, for 33 state, the energy is 18 E, whereas for 1 state, the energy is 2 E. So their difference is 16 E. Similarly, for excitation from anywhere between 1 to 32, his energy will be 11 E. Similarly, if I excite from 1 to 3 I will get the energy in between 8 E. Okay. So from 1 I can see the energy 16 E, 16 E, 11 E, 8 E, similar 1 to 3 to 6 E, and 3 E. So 1, 2, 3, 4, 5 transition from 1 to 1 from first 1 state. Now the second step E21. So from 2 1 I can see the transition can be possible to 3 3, similar to 3 2, 3 1, and 2 2 stage. Okay. So now we have calculated. So 3 2 2 2 1 to 3 3. So that is your 5E to 18E. So your difference will be 13E. Okay. So this is 13E. Okay. So similar process we looked at all the transition from two uh, to one state, and you can see similar. But when we can excite from 2 1 to 3 2 state, so this is how much 5e, and this is so your difference will be 80, which is similar to 1 to 3 1 state. So these two transition will not be distinguished. So we can take this is actually similar to 1 1 to 3 1 state, which is indistinguishable. Okay, so we cannot consider it. Similar 2 1 to 3 1. So this is 5e to 10. So distinguished transition is 5e. Okay. Okay. So and another is 2 1 plus 5e to 8e transition, that is 3e, that is all already observed in case of transition between 1 1 to 2 1. Okay. Similarly, we also derive for 1 3 to 3 3 2 3 2 to 3 1 3 t. So we will see the overall picture, the number of transition, that is will be 16e, 13e, 11e, 6, 18e, 5e, 6e, 3e, 2e, 2e, and 10e. So if I look at, that is total 9 distinguishable transition. So distinguish. So in case of Li, 1, 2, 3 for particle in 2D box with Lx and Ly, we will see 9 distinguishable transition. Okay. So these are the number of number of possible transition state for a particle in a two-dimensional box where Lx and Ly is same, and the quantum number is 1, 2, and 3. Okay. So moving on to the third question: what are the correct statement for the stationary state? So, so stationary, what is the meaning of stationary state? The probability is is not change with temperature, with time. Okay, sorry, not temperature, it's time. Okay, so so change in the wave function psi t psi x plus phi t. We start now. If you integrate, what we'll get is nothing but x squared. Okay, so the probabilities doesn't depend on time. So in this case, just any state called stationary state, if they are if their probability doesn't change with time. Okay, so now the question is comes the correct statements about about the stationary state. Psi xt is an R. The first option is potential energy depends on position x and independent of t. So if you go through the lecture, you can see that the only in case of in case of time stationary states, the potential energy is not dependent on time. So you can say that V x comma t is equal to Vx. So there is no dependence on the potential energy surface. So with this, you can say that in case, and it is only solvable. The the psi xt term only comes when the v is independent of time. Okay, so potential energy surface in case of stationary state is independent of time. Okay, now as I mentioned previously, the state can be called as stationary state if their energy is if their the probability is independent of time. Probability is nothing but this value. Okay, psi xt square in modulus. Okay, so they are in the probabilities doesn't change with time. Okay. Now the third question is system experience no time dependent external force. So if a system say, experience a time dependent external force, then what will happen? The system must be evolved. Okay. Now if a system evolves with the time, then the probability should not be changed with will change with the time. Okay, so if the probability is change with time, the system no longer in a stationary state. So, so that means the system uh, should not feel any time dependent external force. Now, this is the thing that we'll see the that we'll see in the picture when we incorporate time dependent perturbation while the molecule is excited. Okay, so when a molecule getting excited, the first thing is the excitation which is time dependent, and as a result, the molecule will evolve with time. So, and the molecule will no longer will be in stationary state. Okay, now the third question. So the in that view, the third question and third point is also correct. Now the fourth point. This kind of particle is at rest as stationary state. No, the particle should not be in rest. The probability is not dependent on time. That doesn't mean the particle is in rest. Okay, so don't think in that in expression that the particle in rest, their probability in finding in between the range is not change with time, but doesn't mean that particle is in rest. Okay, so in case of for question number three, we can see that first three options are correct, and the fourth one is not according to their question. That okay. Now the fourth question. That is a linear operator among the following. So linear operator, what we say that if a operator, they can say that these. So the psi is a combination of two wave function. Then if a wave function is linear, then if I operate a function operator with a one, then must be work with both the function and give a eigenvalue. Okay. So now with this, we can see what will be what will be linear operator. As you can see that I have already chosen x squared d by dx and d2 and dx2 as a linear operator, but x squared plus y squared is not a linear operator because if I use dx squared, you can see the yeah if I use the x square, it will work on both the psi 1 and psi 2 part. Similarly, ddx, if I use that, ddx will work on psi 1 and psi 2, and similarly d2x and dx2. But if I use x square and x plus y whole square, then there will be cross term. There will be terms called xy and yx. Then it might not. give you the eigenvalue. So x square plus y square is not an linear operator. Okay. So now coming to the question number 5. The eigenfunction of the operator d2x and dx2 is R. Okay. So now if I look at d2x and dx2, so something is any operator can call be eigen if I work on this operator and get back the same value operator with a value. Okay, so this is called eigenvalue and this is eigenfunction of operator A. Okay. Now if I do it of equation, so you will get of 2x. So there is no x square, so this is not an eigenvalue equation. Similarly, if we take d2x by x square of cos x, so first derivative will give you minus of sin x, and second derivative will give you minus of cos x. So you will get minus 1. If I take side as cos x, then d2 psi dx2 will give you minus 1 into psi. Okay, so your eigenvalue is minus 1. So cos x is a eigenvalue, eigenfunction of a, and function of d2 dx2. Okay, so now, okay, now in similar we can see that if I use this equation with e to the power sin x, we get a eigenvalue minus 9. Okay, but si- similarly, if I work it this on x 1 by x, okay, so d, so we will not get the same value. Okay, so that's what we can say that you can see the value. You can what if I do it. So we gonna recover this value. So with that, we can say that this this is a not eigenfunction of x 1 by x square 1 by x. Okay. So now let's moving to the sixth question. So with this we can say that in previous case there is a two options correct. One is 2 and 3. The psi should be cos x and e to the power minus 3ix. In this case the psi is eigenvalue for the d2x and dx2 operator. Okay. So now let's moving to the next question, and we can found the question is that P and Q are two linear operator, and given PQ is minus h IH, the two uh, the correct values of the QP square commutator will be. So for this we have to look at what is the roots of commutator. So if A and B are commute each other, then the A and B commutator should be minus of B and A commutator. Similarly, we can use these are the E comma B into C. It will be A E commutator into C. Similarly, B commutator into A into C. And is a third thing, A plus B commutes with C plus D. Then we can write in a four different parts. Similarly, A into B, if it commutes with C into D, I also can write using the same, you can use this like this and divide into four different parts. Okay, so now for this answering this question, we don't need to so much rules. So just using this normal simple rule, A comma B is equal to minus of p comma a comma b is equal to minus of b comma a. Okay, so the question is saying that p comma q is minus of I h. So now if I divide q p square, so we can write it q p into p. Okay, so we can write it q p into p plus p into cube into p. So now q into p, as I said, then q plus p will be class of I comma h. So now I comma h into p plus p into I comma h. So it will be I. So the third option is actually correct. So so you can see the third option is selected as the correct option. Okay. Now moving to the seventh, that is actually talking about the angular momentum operator. Okay, the pair of observable which can be assigned definite values simultaneously. So for a pair of operator uh, uh, should be assigned simultaneously. For that, the operator must be commutes with other. Okay, so any operator is so some like A and B. If their commutation is zero, then we can we can assign these two operators simultaneously. Okay. Now there is four different option. Now what is The question is what is L? So in vectorial form, you can take that L is R cross P, and P value we know Px, Py, and Pz three different axes. And if I solve the matrix, we will get the Lx, Ly, and Lz values. Okay, these are the Lx, Ly, and Lz values. Now this is the L square value, that is the Lx square, Ly square, and Lz square. Now the question is that how to do assign these two operator simultaneously. That means the two operators should be commute with each other. Okay. So now if I take the commutation in Lz and Lx, okay. So as I mentioned, the Lz is this is the operator for the Lz, x py and y px. Now if I consider their commutation, and you can see if I use the law of commutation, we can see the xpy minus ypx commutes with x. Then you can divide in two parts, xpyx and ypyx. So now x and x will give you value of 0, xpyx and y minus px, and px and y0. Now the question is that this value is coming to the 0, but Lzx is not. Now these two values Pyx is no is equal to 0 because it just think it physically, something is moving on y direction has some momentum that is totally orthogonal to the x direction. So you can think, just physically think that Pyx will be should be 0. Okay, but in some molecule is moving to x direction, have a momentum around x direction, and position is x direction. That now that this value, this px is square, px is 0 value should not be 0. As said, should be not be 0. You can derive it the value. You will not get this px x commutator value 0. So Lz and x should not be 0 quantity. So you cannot measure Lz and x value precisely simultaneously. Okay. Okay, the second option that is says Lx square x square. Now Lx square x square, how we can say Lx into Lx and x into x. So we use the rule of similar rule and divide it into four different parts. And you can see Lx, all the cases Lx is commuted with x, and you can get the value 0. So that means we can precisely and simultaneously assign the value Lx square, and x square. Okay. Now coming to the Lx into Ly. Now if I do the commutation of Lx and Ly, and we will get using uh, all these mathematics that you can do in your room, or you can go through the slides. We will get a value something called IH cut LZ. Okay, so this value is not equal to 0. Okay, so that means if these two values not equal to 0, that means you cannot simultaneously simultaneously measure these two values. Okay, so Lx and Ly cannot be measured precisely simultaneously. Now, if I look at Lx square and x, I can see that L square can be written as Lx square, Ly square, and Lz square. And now, if I look at then doing all the mathematics, I can show it here. Just just it boils to the value where this value goes to the 0. Okay, so L square commuting with the Lx, and that's why you can measure the L square and Lx simultaneously. So therefore, in case of question number 7, only Lx square and x square and L square and x, these two value can be measured or simultaneously. Okay. With this, we will take a short break and we for 5 minutes, and I'll be back. Hello. Okay. So now what we start from where we left. So uh, we are discussing the properties of commutation. So now we will look at the question number 8. What it says that what were the incorrect statements among the following? So Lx commutes with H is not equal to 0, and second one, in quantum mechanics observable L and Lx cannot be specified simultaneously with great precision. The fourth one, Lx is minus of IH cut y dy dz and minus z d by dy, and Lx and Ly is 0. Okay. Now question is that what is incorrect. So with this, as I mentioned previously, I can see that uh, Lx and Ly has a with this all. Is the questions of the your question number 0, because I start a little bit late and we are assigned to do the from the initial part. So in the first class I want to cover as much we can, and so that in the next session we can start with the what is going on. Okay. So these are the this is the first session because we have not notified it previously that the class is already has been started. Okay, okay. So what is the what is the week are going on right now? Uh, hello, hello. Which weeks are going on right now? So that I next class I will go start from there only. Okay, okay. So it will be easy, useful for you. Yeah. So actually, we are looking at in this course. So you are starting right now, no? So in this course, we actually looking at the quantum mechanical picture of how a molecule can excite. So it this course will give a view that how the time dependent perturbation leads to excite a molecule. Okay, so now we just it's a preliminary phase of a molecule so that you are familiar with the different type of operators. Okay, so the assignment number 0 is nothing but a introduction of quantum mechanics, and the later on assignment number 1, 2, and 3, that will you will gradually go up to the how a molecule can excite in terms of time dependent perturbation. Okay, so 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 let me in this lecture let me go through the previous one because I have to go a little bit faster. Just I will upload these all these uh, PDFs. Okay, so now I just go to the lecture that is already I have done for you your help, and that is question assignment number 0, and you can see that the question number 8 what is I am just discussing the question number 8 what it says that the incorrect statements among the following where you can say that Lx comma h not equal to 0. So Lx comma Lx can so if you look at the Hamiltonian, so not in Cartesian coordinates, polar coordinate, you will see the full uh, uh, expression of Hamiltonian comprised of our distance from the origin, angular momentum, and potential. Okay, so now the angular momentum is there. Then you know that now if I consider Lx is with this value position value that is 0, we know. Now if I consider Lx with Lx L square that I showed previously, that is also 0, and it is you know that the L cannot be commute with its commute is V0. So what we can see Lx H are are the two independent operators that can be measured simultaneously. So Lx and Hamiltonian must be commute each other. So Lx is 0 cannot be 0. So that means the first option is incorrect. Okay. And the second thing is that in quantum mechanics, the observable L and Lx can be specified simultaneously. So now L and Lx is can so simultaneously if you want to see that things that means they should be measured precisely. That means they should be commute with each other. Okay, so now if you take the L and LA commutation, you will get the value 0. Okay, so that you have to do, but if you do it, you will get that the total quantum number will be commute with the quantum number along the x-axis. Okay, so that means you can we can simultaneously measure the L value and x value. Okay, now the question is that Lx, what is the expression of Lx? So as I derived it previously, L is a R cross P. So the value of Lx should be I into y h cut into ypz and z minus py. Okay, so this third option is also correct, and the last answer Lx in Ly. So Lx comma Ly, as I mentioned previously, that I have already derived in the previous question that Lx comma Ly is yield yih Lz. That means they are cannot be measured simultaneously, and they have some value that is not equal to 0. So so that option is also incorrect. So for question number 8, the option first and fourth are the incorrect options. Okay. Now moving to question number 9. For an operator A is is a Hermitian operator, and A dagger is the adjoint. The incorrect statement the following is are. Okay. So now, ah, mm-hmm, mm-hmm, mm-hmm. Okay. Okay. So there is so many. Yes, yes, yes. Mm-hmm. And this lecture actually starts with the we start with the basic and it goes to the very high comparatively high level. Okay, so I will suggest you for the basic thing you can look at Mike McCurry Simon books, or for you can also look at the KL Kapoor volume 4. Okay, okay, so you can look at these are the uh, McCurry Simon and KL Kapoor, but further you need to read uh, Ira and Levine molecular spectroscopy book. Okay, for this course. Okay, that is important to look at. Okay, but for clearing the basics, you can look at the McCurry and Simon and the fourth volume of KL Kapoor to look at what is the value of L and what is H and LX, LY, and all these things. That is a very clearly written on that books. Okay, just go through it. Okay, just go through it, and next class you can ask me all about this also. Okay, okay. That this is thing. This. Hmm, hmm, hmm. Yes, yes, yes. But this course is not a basic quantum chemistry course. Okay, so the professor will like to go through the more details about the molecular spectroscopy part rather than the quantum chemistry part. Okay, so we use the quantum chemistry operator to derive the molecular spectroscopy phenomena. Okay, so for that you just clear the basics. You can use the first two three chapter of McCurdy Simon. Okay, okay, okay. Mm-hmm. Mm-hmm. Okay, 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 okay. But look at this these papers, these books. Okay, for a message box. Okay, I will write down. Okay, once I finish that, I will write down. Okay. And you can look at this NPTEL forum in this course CY whatever for 25 or 42. It is written over that what are the necessity books or for this course. Okay. So here it is mentioned what are the books are needed to read for these courses. Okay. Anyway, I will write. Okay. Hmm. So I am going a little bit further because fast because I have to finish it. Otherwise, I started late and the time is not there. Yeah. Mhm. Because after the time I have to catch up what is the left. No. So the question is come this is a Hermitian operator and A dagger is it adjoint. The incorrect So any operator can be called as Hermitian if its adjoint is equal to its actual value. Okay. So with that, we can say that if we go to the all the rules of the Hermitian operator, you can see that A and A prime is a Hermitian operator. Similarly, A, A adjoint, sorry, A into A adjoint and A adjoint into A is also Hermitian. And the summation between A and A prime is Hermitian, but these things A, A and A minus will not follow the rule of Hermitians. Okay, so this in this case, uh, in this case, it will not follow the Hermitian operator. Okay, so now going through the last questions of the of question number 0. For an operator, the function of orthonormal psi 1. Okay, so let's clear about the idea of what is the orthonormal function. So orthonormal function, suppose the psi I and psi j are two functions that are called as orthonormal. So orthonormal means if I take psi I and psi I, similarly psi j and psi j that are normalized. Similarly, if I take projection of psi I on psi j and projection of psi j on psi I, it will be 0. So now you can say psi I and psi j are orthonormal set. Okay. Now with this concept, uh, we can use this equation for what we say that what is the for an operator A and set of orthonormal wave functions psi 1, psi 2, psi 3 are defined as a function such that A psi 1 is equal to psi 2, A psi 2 is defined as psi 3, and A psi 3 is defined as the psi 1. The expectation value of superimposition of psi. Okay. So now, okay, so if you if sometime if you are given a wave function that is in like that the combination of three different linear combination of three different wave function, so first we have to check whether the wave function is normalized or not. So if it so in quantum mechanics we have to check the wave function is normalized or not. If it non-normalized, then our first step is to normalize that wave function. Okay, so first we check the whether the wave function is normalized or not. So for that we take the uh, psi with the integration between psi and psi, and what we get the value we can see with that equation uh, that the value is corresponding to 1. That means within the space the psi is normalized. Okay, now what we get now once the psi is normalized, we have to get the expectation value. That is, psi should be projected on a should psi should be the value of psi will be so so the now first we have to look the value on operation of a on psi. Okay, so now if I operate the psi 1 A1 with psi 1, we will get the value of psi 2 with the eigenvalue of half. Similarly, if I projected the value operate A with the psi 2, we will get the value of psi 3 and similarly psi 1. Okay. Now, once we get this part is done, so this part result like this. Now we projected on the in psi part. So this is the actual equation looks like after if you operate with the operator A. Now if I look at the equation, yeah, and we can say the rule that the psi 1, psi 2, and psi 3 are orthonormal to each other. So if in any case we are get a cost term between psi 1 and psi 2, or psi 1 and psi 3, and or psi 2 and psi 3 like that, the terms will be zero. Okay. So with this we will get the value. What would they get? Psi 1 operating with psi 1. Similarly, psi 2 is operating with psi 2, and psi 3 is operating with psi 3. And as a result, we will get psi 2 and psi 1 and psi 1 will get to 1 by 4 as they are normalized. So psi 1 and psi 1 will give you psi 1, psi 2, and psi 3 will give you value of 1. So all the cases will get for psi 1 and psi 1, I'll get the eigenvalue 1.4. Similarly, root 1 by 2 multiplied with 2, 2 root 2 and 2 root 2, and we'll get 1 by 4, 1 by root 2. Okay, so with this, we can say that in this case, the second value is correct. Okay, so this is the answer of the your assignment number 0. Okay, so these are the all answers of assignment number 0. I will upload all this video, all this PDF file in the link, and you will get the um, will get from there. So now connect my charger. Now let's quickly go through what we can we can cover through within this time scale in assignment number 1. So now assignment number 1, we have evolved through we know that we have know that the uh, the time dependent wave function. As you can see that if you have a wave function that depend on the both pace and time, you can write at a psi x comma t, and from there you can do that this operation which is called a standing wave operation, or standing wave equation, and from here you can go through with this literature and you derive the time dependent Schrodinger equation, which is nothing but written like this. So I cut d psi xt dt is e psi xt. Okay, so that is very important for this course, time dependent Schrodinger equation, that is written as TDS. Okay, and on another side you will get a momentum operator value. So you can see that in classical mechanics, momentum is nothing but P m into V. Okay, so V is nothing but d by dt. But in quantum mechanics, it's transformed into d by dx. Okay, so that is the change. Okay, so now Now let's start with the question number one. What is the correct or statement about the following thing? The independent Schrodinger equation is a total energy value equation. That is true because you can see that here is the total energy which depends on the kinetic energy as well as uh, potential energy. And now the second question is I h का d by dx psi xt is equal to psi e psi xt. So I have told it is a time dependent Schrodinger equation that value incorporate d by dt e psi xt. So with that you can see this is a d by dx. So this is a incorrect option. Okay. Similarly, the second thing is that I h car d by dt is written as px psi xt. So as I mentioned, the px is a operator dependent on the and in quantum mechanics dependent on the position. So this is also incorrect. Now, the fourth option is saying that for a given eigenvalue equation, psi square psi is equal to psi, is where psi is an wave function and c is quantum mechanical operator with possible value plus 1 and minus 1. Okay, so now if I take, let's understand the things like that, psi is equal to a into psi. Okay, now c into psi is equal to c square psi is equal to psi. It is in the question. Okay. Now, if c into psi, psi is a eigen function of c, then c psi will be give you the value of, let's say, small c into psi. So now c is the eigenvalue and psi will be called as eigenfunction of operator c. Okay. So now you can think like this c into c over psi. Okay. Now c psi is equal to c comma psi. Now c I can take out and now we operate c psi that will give you the value c into psi. So c square is equal to psi and that is equal to 1. So c square 1. So c should be plus 1 or minus 1. Okay. So with this we can say that the option that given is in option number 4, that is for a given eigenvalue equation c square psi is equal to psi, where psi is an eigenfunction of eigenfunction and the c is the quantum mechanical operator with a possible value psi 1 and psi minus 1 is a correct option. Okay, so now and you can uh, okay, so now question number 2. The correct statements about the time-dependent Schrodinger equation among the following is are. The first option is saying that IH cut d by dt psi xt is equal to h psi xt. So we know that h psi xt is nothing but e psi xt. So h psi xt nothing but e psi xt. And with that formula, we can say that the option number A, which says as I h cut d by dt is nothing but E psi xt. Okay. Now the second question is that for a quantum state psi x comma t, the time dependency is governed by the total energy operator of psi x comma t. That is also true. And now the fourth option is giving that kinetic energy operator depends on the position of x as well as the time. Okay. So now if I let's move to the first slide. Mm. So Px is I can say that it is independent of time. Similarly, if I look at the kinetic energy part, it's nothing but Px square by 2m. So what we can see that minus h cut by 2m, it will be your d2x by dx2. It is your kinetic energy operator. Okay. So now, so for this case, we can say that the time kinetic energy operator is also independent of time and only depend on the position. Okay. So this statement is incorrect. Similarly, potential energy operator can never be independent of time. So uh, if I if I say previously the potential energy operator, if it independent of time, you can say that in a, if we derive the time dependent Schrodinger equation, whatever, you will get a something called stationary state. Okay. Now, something like this, if you excite a molecule, okay. Now the excitation will go through its will change the potential energy circle. But that means the potential will change and and it will stay depending on the time. Okay, so potential energy when molecule is excited, getting excited, then the potential energy cannot be independent of time. It must be dependent on the time. Okay, so while excitation and or any other perturbative potential that is dependent on time, the potential energy operator cannot be independent of the time. Okay, so only in case of stationary state and for the beginning case, we can see that Vxt is equal to Vx, but not all the cases it is independent of time. Okay, so this is also incorrect. Okay. Now question number three, what it says, what are the correct statements about the Hamiltonian operator among the following is and are? A generalized Hamiltonian can be written as a combination of Vx comma t plus h cut 2m dx2 by dx d2 by dx2. Now I have told that h is a h is a total energy operator is a combination of T and V. Now I have written that T is minus H cut 2m d2x by dx2 plus Vx comma V operator can be written as Vx comma T. So what we can say that so this this is for this is a incorrect option. Okay. So now going to the second thing, for a harmonic oscillator, H half f x square minus H comma d H cuts by 2m d2x dx2. So in harmonic oscillator, you can see the force is written as minus of kx square kx. Now, if I want to, from force, if you want to get the potential, you have to derive it with respect to the position. Okay, so minus of dv dx is actually the force. So if I get the minus of dv dx is equal to kx, now you have to integrate it. You will get the potential energy value half kx square. Now if I incorporate the potential energy value with the in the Hamiltonian, we will get the total Hamiltonian is minus of h cut square by 2m dx2 by d2x d square by dx2 is plus half x square is equal to full to Hamiltonian value. So with this, your second option is correct. Okay. Now, a third one, for a free particle, h cut vx minus h cut square m by 2m d2x by dx2 had vx is not equal to 0. Now the question is what is called free particle? Now the question is that the what is called free particle is like that a particle can be called free when there is it can move without any other external influence. Okay, so if I look at the potential particle in a box, so you can see that within the box the applied potential is zero, and be, uh, and above the wall of the box the potential energy is infinite. So particle in a one-dimensional box is a free particle because it doesn't experience any potential. So for a free particle, so in a particle in a free particle, it doesn't experience any potential. So Vx for a free particle should be zero. Okay. So with this, you can say that the C particle option number C is a incorrect option. Okay, now coming to the question number D, the Hamiltonian operator H represent the difference of kinetic energy and potential energy operator. So Hamiltonian is not a difference, is a addition of potential energy and kinetic energy operator. Okay, so this is also incorrect. Now moving to question number 4, it says the correct statements about the following and is a now overlap integral of between state 1 and 2 for a particle and one-dimensional box is 0. Second thing is that action integral of particle operator A is represented as psi n, A psi n. Now overlap integral between psi m and psi n is given by S, and expectation value of operator A is given as psi m A psi n. Okay, so now if we just start with the particle in a one-dimensional box. So in particle in one-dimensional box, I have sent it previously the in particle in one-dimensional box above the boundary beyond the boundary the potential is infinite, and in the boundary the potential is zero. So if I use the equation, total full Hamiltonian is H is combination of T plus V. The V will be zero within the box. So Hamiltonian can be written as the only the kinetic energy part. Now if I solve it using the equation, we will get psi x is equal to sine n pi x into L with some normalization constant that we have to derive. So now how we can derive? So in a so what I can see that the molecule is within the box and the box length is L. So we have to consider the normalization within these within this length. So we integrate the value of psi between 0 and L, and see, as we can know that in 0 and L, you will definitely find the molecule. So probability of the finding the molecule between 0 and 1, 0 and L or within the box is 1. So now we have integrate the value within 0 and L, and what we will get the C square value, as you can say, is root of our 2 by L. Okay. So now and the nature and the wave function is full wave function is look like this. So this is a total norm is a normalized wave function where n is the quantum number and corresponding energy is given by En, which is n square h square by n square. Okay. Now if I look at what will be the nature of wave function for different n values, so what we'll get, so for n equal to 1, it will look like that. N equal to 2, you will get a node, and n equal to 3, you will go get like this for n equal to n equal to 3. Now question comes, what is the overlap between the psi 1 and psi 2? Now for overlap integral, you can take a psi 2 and we can set the psi 2 and psi 1. Okay. So now and anyway we have to integrate in between 0 to L, and what we will get? You put the value of n2 for psi 2 and 1 for the psi 1. And now if I integrate between 0 to L, you will get the value that is equal to 0. That means the overlap between psi 2 and psi 1 or quantum state 2 and 1 is 0. There is no overlap. Okay. So in physically how we can view it's something like that. If I just overlap this wave function with this wave function, you can say this part will will neutralize the other part, and as a result, your overlap between psi 2 and psi 1 state vanishes. And you can think it normally, and you don't need to solve this equation. Solving the equation is a different way to get the answer, but without solving the answer, if you just think it overlapping between psi 1 psi 2 and psi 1 state, you will get the value, the overlapping value, the total net value is 0. That means the psi 2 is not overlapping with psi 1. Okay. So first question, the first option, the integral overlap integral between psi 1 and psi 2 in one dimensional box is 0 is the correct option. Now the question is that action integral of operator a prime a is represented as psi n and a prime psi. Now action integral means something that can occur that can act is in an operator and that will move. But if it's some in same operator, that means there is nothing happened in that operator because the final state and initial state are same. That means the action operator doesn't do anything. So that means the B option number B is incorrect. So now going to the option number C, the overlap integral between psi m and psi n is given by psi m and psi n is. So I can show you the previously for deriving the overlap between psi 2 and psi n. So psi 1. So that means that option number C is correct. And now the expectation value, the fourth option, the expectation value for operator A prime is given by psi m a comma psi n. Now expectation value means it's occur only in a particular state. So expectation value is so expectation value for a particular state, comma let's say psi n state is can be written as in Okay. Now, if psi n is normalized, you can retain as expectation value of psi. So it's not like psi m a operator psi n. That will be some action operator, action integral. So except expectation value should be psi n comma psi n a psi n, not psi m a psi n. So with this is also incorrect. Okay. So now moving to the question number four. Sorry, five. So for a free particle, the quantities that show time dependence among the following is are. So if you go to the lecture, so what is this? Any operator that is commutes with the Hamiltonian will not uh, will not show the uh, time dependence evolution. Okay. So with this, you can see that if you go, this needs a rigorous mathematics to answer this question. That you can go through that, and you will get the answer that these three is the correct options for that question. Okay, so that is you can do it in home and check whether it is correct or not. Okay, so now question number six. The correct statements about the Hermitian operator among the following is and are. Okay, so A, the if the Hamiltonian operator, this Hamiltonian operators commute, then they cannot process any common set of eigenfunction. Okay, so um, now the question is second thing is that all the eigenvalues of Hermitian operator must be real numbers. C, the if A or G and G A F star is a valid, then F and G are the eigenfunction of the Hermitian operator A dagger, and and the fourth one, the quantities F A G and F G are a number. Okay, so now let's start with the equation F expectation the action of integral between F and G. Okay, so now if I take if I consider psi star F A G and we can construct and take the uh, that value we can get, you can write it something like this. Then you can see F and G are eigen functions of Hermitian A. Okay. Now, so with this, uh, and another thing, if two Hermitian are commutes, okay, they can possess common set of eigenfunction. Okay. So with this, we can say the option B and C and D that are the correct statements of the following. Okay. Now going to the question number seven. For an unpart of two level systems, a state system is given by psi t a1 psi 1 e I e1 t h bar psi a2 psi 2 e I2 h card. The correct statement is the following. Okay. Before is going to the deep whole discussion. Now the thing is that why we retain the wave function is a linear combination of two different states. Okay. Now take a system in a ground state. So in ground state, you can express the wave function in a single wave function. Okay. Now, if I excite a molecule in a time dependent manner, so what will happen? Now the molecule can either be in ground state or be in excited state. So in a particular, so you cannot define the molecule with a single wave function. So it a linear combination of excited state as well as ground state. So that's what you can say that psi t you can take it like this. Okay. Now, what he says for the unperturbed Hamiltonian H, so when light is not not applied, then what is a unperturbed Hamiltonian H0 is written by H0 psi 1 E1 psi 1 H0 psi 2 E0 psi 2. But it's a correct because the light is not important, that is time independent Schrodinger equation. You will get the value of H psi is equal to E psi. Okay. Now the second option is the orthonormality. Psi 1 and psi 2 depends on the nature of psi 0. So now these are the eigenfunction of H0. So it must be orthonormal to each other. So the B is incorrect option. Okay. Now C, what is it? The A squared is the probability of finding the finding for that the measurement of the energy will would lead to E1. So you can see that the as I mentioned that E1 is corresponding to the energy level that is one state, and E2 the corresponding to energy level that is the two state. Okay, and they both are orthogonal to each other. So if I look at the probability of finding in probability of finding in molecule, you can see that uh, the A square is actually the value that measures the um, molecule to be in a state that has an energy of E1, and A2 square is a probability that the finding of a particle that they stay in E2 state. Okay, so with this the option C is correct, and if psi t is normalized, then A square, A1 square, and A2 is 1. So for this, you need a little bit of mathematics, and you can see that how we can do it. So that is the you can see we can write psi 1 and psi 1, and we did the full we break it in a linear combination of it, and we can see that a1 psi 1 into a1 psi 1 a1 psi 1 a2 psi 2 a2 psi 2 into a1 psi 1 and a2 psi 2 into a2 psi 2. Now what is happened, a1 psi 1 into a1 a2 psi 2 will give you zero value because they are orthonormal to each other. Similarly, 8 psi 2 into psi 1 also give you value 0, but these two will give you the value of psi a1 square and a2 square. So what we will get, psi 1 square and psi 2 square is a 1 value. Okay, because the whole normal whole molecule whole wave function is normalized. Okay, so with this function is also correct. Okay. Now going to question number 8. The time dependent perturbation H comma T is a turned on for two level system described in question number 7. Okay. The correct statements is among the following is are A1 and A2 is function of time T. That is correct because you consider these are a time dependent function time dependent coefficient. Second thing is the A1 and A2 hot. Okay, so that is eventually A1 and A2 are non function of is a non-function of time is not incorrect. Okay, so now yes, hello, hello. Okay, so now thing is that psi 1 H comma T psi 1 is not equal to 0. What does it mean? That if you look at this H comma T is a perturbation Hamiltonian. Okay, now so now think that you are if you are in a psi one state, the first state. Okay, now you are applying a perturbation Hamiltonian that is H comma T. Now if after the perturbation you are in a same state. Now that doesn't that actually not says that you are in a same state with perturbation. That means nothing. Okay, so if you are excitation. considering, but if you are in the same state, that means you are not getting excited with this perturbation. So this with this that value psi 1 is not uh, 0, that means no excitation yields nothing. Okay, so this is also incorrect. And uh, then D is, if H comma T is Hermitian, then psi 1 H comma T psi 2 is equal to psi 2 H comma T psi 1. So if you think this is a two level of system, then if you are exciting from one perturbation, time dependent perturbation from 1 to 2, then eventually you can get back 2 to 1. It is a similar way. So these two can be equal. So this equation is also correct. Now question number 9 is says the momentum p of a particle uh, with length of with length of wave vector k 2 pi by lambda is given like this for wave function. Okay, so lambda is h by p is coming from de Broglie equation, uh, which is nothing but a particle duality. So now, if I say k is equal to, k is a wave vector, that is 2 by lambda. Now you can substitute the value lambda by 2 pi by k. You will get equation p is equal to h bar k. Using this all the formula that I show it here. So and for that you can see that the number option number C is correct for this question. Okay. So now moving to the last question of this assignment number one, the x component of angular momentum px is the given by px I h car d by dx, and the commutator x px I is equal to I k I h bar. The correct statement is an r delta a and into delta b is greater than or equal to 1 by 2 y a or b commutator. That is a hint. So now, what is the option there? The state function psi cannot be simultaneously eigenfunction of x and px. Okay, the precise value on x and px can be assigned simultaneously. Delta x into delta p is 0. Delta x and delta p is a high, greater than half pi, half into h pi. Now, if you look at uh, x delta x into delta p, that is given at using the value xp. Okay, so now x comma, if I look at x px is nothing but I h cut. So the value will be h cut by 2. That is your option D is correct. Okay, so now on the similar note, the ix is not commuting with px, then option C is also incorrect, because if it's not commuting with p, x is not commuting with p, then x px x commutation will not be 0. As a result, delta x into delta p x not equal to 0. Okay, so option C is incorrect. Now the precise value on x and px can be simultaneously assigned. Now, as I mentioned previously, if two commutator uh, if two operator commutes with each other, then you can measure these two value simultaneously. Now x and px is not commute with each other, so you cannot precise simultaneously measure both the position as well as both the momentum. Now it rings a bell if you don't this thing actually tells that if for a particle like very tiny particle you cannot measure the position and position and momentum. That is nothing but your Heisenberg uncertainty principle. Okay, so from here, from this relationship, it comes into the picture, and it says that for a very tiny particle or quantum mechanical particle, you cannot measure the time and position, sorry, position as well as momentum simultaneously. Okay. Now the first option is that the state function psi cannot be simultaneous eigenfunction of x and px. So the same argument I can say that the x and px are not commuting with each other. So the psi, if I operate with uh, x on psi and operate with px, psi on px, that will give you the different values or eigenvalues. So we cannot simultaneously get the same eigenvalues. We cannot be get simultaneous eigenvalues. So option A and option D are correct from the question number 3. With this, we are going to conclude this session. Okay. So the next session, I will be complete the next two lectures, 2 and 3, assignment 2 and 3, and I'll try to catch up whatever going on in the class. Okay, so I am going to stop here right now. Uh, if you have any question, you can ask, or I will share the. Let me write the books that are needed for the courses. So you can go to Ira in Levine. Okay, but this is for molecular spectroscopy. Okay, uh, MC Cody and Simon. You will just look at the, maybe I am wrong with the spelling, just look at, okay, quantum chemistry, physics, and you can look at the KL Kapoor, fourth volume, okay. So these are the books, but this second two means McCody Simon and KL Kapoor is for only basics of the quantum chemistry. But understanding this book, this course, the Ira Levine is the most important. Okay, okay. So with this, I am stopping it here. Okay, let's meet in next week. Okay.